Right, sorry for the delay starting. I have a talk that was going to push up right against the end of time, and we're starting 7 minutes late, so I'm going to talk really, really fast. So this is a talk about everything I know about functions, and it's certainly more than any one person would ever want to know about Python functions. My name is Mark Smith. I work for Nexmo. I am GD2K on pretty much every social network. I am a developer advocate. Nexmo, who are paying for me to be here, so I'll give you a little brief blurb, provide web-based APIs that allow web developers to write code that sends text messages, makes phone calls, or sends messages via different streaming platforms, instant messaging platforms. We also supply video streaming components to allow you to build your own mobile apps that send video between different platforms. So that's enough about me and my company, because we really don't have enough time for this. Here's a function. What we're going to do is we're going to build up from the simplest function to some really complex stuff and talk about all the limitations but all the freedoms that Python syntax around functions gives you. So this is about as simple as you can make it. It's a single-line function. We're going to look at lots of variations on this one way or another. We can call it twice, for example. What's very important, and we'll come back to this later, is that in this function definition, this line, the def line, is only ever called once in almost any Python program. Whereas this line is called every single time the function is called. So because we are calling the function twice in the lines below this, this print line will be executed twice, whereas the function definition will only be executed once. We'll come back to that later. Functions are just variables. So here we are defining a variable of type function called sayHello. Here we are assigning it to a new variable called hello. And here we are calling the variable called hello, and it just executes it as if we had executed our function directly. A side effect of this is that you can put functions in lists or dictionaries or sets, anywhere else that you would store a value. Functions that do exactly the same thing every time you call them aren't that useful, so we often define them to take parameters. So here is a function that takes two parameters. Parameters are just variables that can be provided with values or arguments when they're called, and then those values can be accessed as variables inside the function. So here's what it can look like when you call a function, call that function, but I'm just going to take a short diversion. These two things here are parameters. They are essentially placeholders for you to provide values. So they appear in function definitions. These two things here are arguments. They are values that are provided to the function. So here I'm providing two string literals in fact, but they could well be variables where we're passing the values into the function. But those are arguments, and in the definition, they're parameters. I'm almost certainly going to mess this up at some point during the talk, but I'm going to try consistently to talk about these two things with the separate terms. So back to our calling our function. So here we are calling we are passing the parameters. I've already done it once, see? We are passing the arguments by position. So the first argument is provided to the first parameter, and the second argument is provided to the second parameter. Simple enough. We can also call them by name, or pass them by name. So here we are passing the value for the recipient parameter by name and the message parameter by name. When you do this, they don't have to be passed in order. So we can reverse the order and pass the message first and the recipient second. They will just be assigned to the correct named parameter that will be bound to that parameter when it's called. We can combine the two. So here we are providing the first argument to the first parameter, and then we are explicitly providing a value for the message parameter. The positional arguments are bound first. This is important because for example, in this case, we're providing a positional argument. Sorry, here's our parameter, recipient parameter. We are assigning our first argument to that parameter, and then we are explicitly providing a recipient argument which goes to the same place. And so when you execute this line of code, you get this error message, which is actually pretty straightforward. Got multiple values for the argument recipient, but we know why. The other thing to note is that in a function with this kind of definition, we must provide arguments for all the functions that are there. In JavaScript, this isn't true. But here we are trying to call a function that takes two parameters with no arguments, and so we get an error, again, saying we're missing the arguments that we should have provided. Default arguments like this, look like named arguments, like the ones we've just seen, but they are defined in the definition, not the call. All the calls below this definition are valid. So the first call, the first call misses it out entirely, in which case the default value that's provided in that definition line is used. In the second case, we provide a positional argument, so we're providing 3 positional arguments, and so the third one is bound to the sender parameter. And in the last case, we're providing it explicitly by name. So these are all valid. We can choose to send it or not to send it, and if we do provide it, then we can provide it either by position or name. In a definition, the parameter with the default value must be provided after all the parameters that don't take default values. So this is invalid. So here we have a sender. I'm trying to think, have I got arrows here? Yes. So here the sender parameter is defined with a default value, but there's a message parameter after it that doesn't provide a default value, so this is invalid. So in fact, you'll see here non-default argument follows default argument. So that's saying the message parameter needs to go before sender in this case. A lot of this is kind of intuitive, so you may not know these rules, but you won't have broken them because they just sort of make sense when you define these things. You'll usually come up against these problems when you're modifying the signature of a function, and so you add a default value to a parameter that didn't have one before, and suddenly you'll start getting these errors that are telling you that these things aren't valid. So, yes, next slide. So we're going to talk about mutable default arguments. We're going to go back to that case that I put up on the second slide. So here we have a slightly different version of this function. So I work in SMS, so these are all going to be SMS examples. So here we've got a send many SMS function, which takes a sender, a message, and then a list of recipients. So the idea is you could send a bulk email to all of your friends telling them that we're going to the pub this evening, for example. But if you don't provide, we've provided a default value for the recipient's parameter, just in case, just for a shorthand. This is our best friend, maybe, that we always want to invite to the pub. We can call this without providing a value, in which case it will use the list that we've provided, or we can call it with a list with a specific set of numbers, and that works, right? So we can see that in the first case it's sending it to one person, and in the second case it's sending it to 2 people. But requirements change. And at some point we realize that, in fact, we've got a logging phone. It's a stupid idea, but we've got a logging phone, and so every time we send SMS to our friends, we also want to make sure there's a copy of that SMS sent to our logging phone, just to make sure that we're keeping a copy of it somewhere. So it's easy enough to add a line into our function that modifies the recipient's value. So every time we call the function, it's just going to add this value to the list, and then send the messages out. And that works, so we can see from this function call. But then the second one, when we call it a second time, you see that it sends a message to the logging phone twice. And that is because of what I said at the beginning. Oh, I even have a funny transition there. The reason is, what I said before, is this line, the def line, is executed once, and then that value is actually attached to the function definition. You can get it out if you want to by introspecting the function. And so this recipient's value, this recipient's list, is defined at the beginning of your program when the function is defined. And then every time you call the function, it's appending this value to it. So this is done once, this is done every time you call the function. So every time you call it, it will send like a multiple copy of that message to your logging phone. So we can fix it easily enough, and you'll see this pattern throughout Python code. None is a nice immutable value, so it makes a great default value for a parameter. And here we just check that if it's none, we give it the default value we wanted it to have. And because that's inside our function block, this is executed every time we call the function with a none value, and so it doesn't kind of leak into across function calls. So when we call this, this does what we expect. So we're done, right? No. So in many cases, you won't just be passing in a list. You will be calling it with a list that you already have. So in this case, I have my list of phone numbers, and I'm passing that into the function call. And then when I print out the value of my recipients list, it's been modified afterwards. So that is unexpected behavior in most cases, unless you're calling a function that specifically says, I will modify the arguments that are sent into me. So this is essentially a bug in our code. or at the very least unexpected behavior. So we can fix this by creating, no matter whether it's called with none or with a value, we just create a new value here. We're creating a new recipient's value inside a variable inside the function, and then just adding this our list with a single item to it. So in this case, we're not modifying a list, we're creating a new list and assigning it to the variable. It becomes clearer if we don't modify the existing parameter name. So I recommend never modifying a parameter that's passed in, or at least steering away from it. So in this case, we've created a new variable called allRecipients, and we've created it with a value that makes sense in all cases, and then we're just looping through that and sending the SMS. So this is a proper solution to the problem that we've just come across. So now let's talk about variadic parameters. Don't panic if you haven't heard the word variadic before. I only came across it relatively recently. It's essentially the star args thing, is how it's often referred to in Python. It is a positional parameter that will just mop up any positional arguments that are passed to the function and provide them to your function as a tuple. So in this case, you can see I've defined a kind of fake printf function, and it will take as many parameters as I want to pass it positionally. So it takes at least one format string, and then it takes as many parameters as we want. So if we had some logic in here, pulling out those %s placeholders and inserting the values you've passed in, it's a nice kind of fluent way to define a functional interface. Star args is not itself a parameter, so you can't call printf and pass in a value for args. All it does is it mops up the values that aren't specifically passed in. So this gets an error, unexpected keyword argument. Keyword arguments. So you've probably seen this before as well. I never quite know how to say this out loud. **KW args. It's the equivalent of variadic parameter, but for keyword arguments. So in this case, it mops up any provided named arguments that aren't already provided to sort of properly defined, strictly defined parameters. Anyway, named parameters that we've actually listed. Anything that's provided other than that as a named parameter will be turned into a dictionary and passed in as a KW args variable. And I would normally describe what that program's doing, but I'm not going to this time because we're short of time. So a problem that we often have with functions is that we have a function which just takes a lot of parameters. Some of them are optional, some of them aren't optional. And then somebody will call it like this. In some other languages, like Java, for example, this is the only way to call a function. So if you have a function with too many parameters, it's probably better to extract that out into, say, a builder class or something like that builds up the parameters and then creates your object for you, or calls your function for you. But Python, fortunately, has this nice way of, as we've already mentioned, we can pass in named arguments to our function. Sometimes it's quite nice to enforce this. If you've got a very kind of flexible interface to your function, it's nice to say to people, look, you need to provide these by name, because there's no point in providing 16 parameters by position. Nobody is going to know what those are. This is me sending my friend's phone number to another friend from my own phone. So, in the last case, which one of those is which? Who knows? Whereas this one, it's nice and clear, because we've labeled each of the arguments that we're passing in. So in Python 3, and bear in mind all of this is Python 3 except for one slide, we can provide just an asterisk in our parameter list, and that then means that all the arguments that are provided, all the parameters that are defined after that must be provided as named arguments. It's a really nice thing. So in fact, we're enforcing this now, and this becomes invalid. And it works with parameters that have a default value defined or without, as you can see. So you can combine this feature with a variadic placeholder. You can also put it wherever you want. So in this case, I can call the function with sender, recipient, and message just by position. And then, but the others, let's say more optional or more complicated arguments have to be provided by name. And you can combine this with a variadic, I never know what to call that, placeholder argument, by using a name after the asterisk. So this is just the same as before, but because we're not providing this at the end of the parameter list, we're just saying that, again, the first three arguments can be provided by position, and then we can provide any other arguments we want to by position, but they will never be assigned to any of those parameters that are defined further on unless they're explicitly provided by name. So the problem with variadic parameters and those keyword parameters is that they look very much like this. And we've probably seen this before. What I'm doing is I want to call this function up there, but all my values that I want to pass are in data structures. So I kind of want to unpack them as parameters to my function. So I put all my positional arguments in a tuple, put all my named arguments in a dictionary, and then I can pass all of those in to send SMS. This works, but it's not the same thing as we were just looking at. Those are placeholders in the definition that will pull out values from that you pass in. Whereas in this case, what we're doing is essentially unpacking these positional parameters, arguments, and named arguments, and then just calling the function with those. In some other languages, this is called apply or something like that. It's another method on the function, but in Python, we have a specific syntax for it. It's just kind of the mirror of what we were just looking at. Python functions they return none by default. So if you don't have a return statement, your function will be returning none. I'm sure we've all forgotten to add that return statement to some sort of calculation function. I did it last Thursday. When I first started learning Python, we only had 3 scopes. Somebody told me after the last time I gave this talk that actually there's one more scope, but I would need to go back to pre-Python 2 to find out, and I don't feel like building that for my modern computer. But let's just say there's 3 scopes: built-ins, modules, and functions. And we can access global variables, so variables outside of our function scope, without having to do anything special. So here I've got a function that just does a kind of calculation with this global value, and then returns something useful. That works fine. Also, if we have a mutable value as a global, we can modify it in place. So I'm not assigning to the variable, I'm just kind of modifying it in place. In this case, I'm adding a value to it. That's fine too. Unfortunately, we can't assign to global variables inside a function without going through an extra hoop. So this doesn't work. So here we've got the global value is set to true, we call the function with false, and then afterwards we just print the value of the global variable, and it's still true, it hasn't changed. And the reason is that when you assign to a variable inside a function, that's part of the function definition. It's kind of part of the stack frame. It says, oh, we now have a local variable called useHTTPS, and it has this value. So all we've done is we've created a new variable inside the function, and then the function finishes running, and we no longer have the variable anymore. It's popped off the stack. This can cause some weird stuff. So I don't know if anybody's seen this before. I've had it a few times in my career where this is a thing I point out to people as a really unintuitive thing in Python, in fact. So we have this print statement here. Let's say that works fine on its own if this is a one-line function. But as soon as you add this line underneath to modify the value, suddenly the whole function stops working. You actually get an exception from the print line, not from the modification line. And this is because, as I say, when you assign to this useHTTPS thing in the function definition, it becomes a local variable. And so we're trying to print out a value on the line before that is in fact a local variable that hasn't been given a value yet. And so that's specifically what this error means. It's a weird one. In fact, it's the only case in Python that I can think of where an error is thrown that's caused by a line below it, rather than a line above it, or a line that's been executed before it. So we fix all this by using the global declaration, global statement, sorry. It's just, you use the global keyword followed by a list of variables that you want, where you want to be referring to a global variable rather than a local variable, and it just kind of fixes everything up. So global gives us the ability for a function to assign to a global variable. It gets a bit more complicated these days because that glorious time when everything was simple before, we couldn't define functions inside functions. And now we can. Closures are a really powerful mechanism for kind of passing around executable state. So I will cover the equivalent for closures now. So here we've got a function called getLater. It takes a URL, and then it defines another function called get inside, and then returns it. So that's returned here. It's not executed at this point. So when we call getLater and we pass in a URL, and then we assign that to a variable, we've got a function in that getter variable now. And then here we actually execute it. We don't pass in a value because get, you can see, is defined without taking any arguments. And this all works pretty well. what's weird about this, if you haven't seen it before, is this URL variable was passed into the outer function, and then it's accessed in the inner function. So actually this outer function has completed. By the time we call getter, like getLater is finished and it's already returned its value. But you'll notice that all its state is, well, in this case, for this to work, its state has to still be around. The variables that are defined inside getLater or available to getLater have to be stored until get is called and then disposed of. So this causes some, yeah, there we go. So this is our new 4 scopes. We've got functions, modules, and built-ins. And that blue circle could go on forever because you've got functions inside functions inside functions. Don't do that. So we have a similar problem here to the global variables, where you've got, here we have a variable defined in the outer function, and then in the inner function we're trying to assign to it. But we already know that if we assign to a variable name inside a function, it's going to create a new variable inside that function, which is then, well, it's going to be returned, but it's going to be the same value each time. So the outer value here is never being modified. So it's kind of, if we were to take out the outer function, it's exactly the equivalent of the global thing that we had before. And so we would fix that with the global statement. But if we put our outer function back in, we need to fix it with non-local. So non-local does the equivalent of global for an enclosed function. So now, just to summarize, we have global, which allows a function to talk to a module-level variable. We've got or an inner function to talk to a module-level variable. Or we've got non-local that allows an inner function to talk to assign to an outer functions variable. So I said I'm going really quickly. I'm sorry I can't pause between any of these. So now I'm going to talk about methods. So I'm going to talk over the next kind of 2 or 3 subjects about why this self parameter exists. Because I know that frustrates some Python people. It feels unintuitive, but it's kind of turtles all the way down. And when I discovered how this all worked, it was a bit of a revelation for me. So here we've got this is actually, interestingly, this is a function defined inside a class. So we call them methods. And I'll point out in a minute why this is a function. But you can see it's just the same syntax. We have this first parameter called self. That's just a convention. It doesn't need to be called self. When I first moved from Java to Python in about 2000, I kept on insisting on calling it this because that was just what made sense in my head. And then I got told off by lots of other Python developers, so now I call it self. Yeah, although we've put that in the parameter list of our function that we've defined inside a class, when we call that function, it's not there, right? It's there. So that's a bit weird. So we're calling it on the instance, but then we don't let self's there. It sort of automatically moves it over into our argument list. And I'm going to talk about why that works. I'm going to try and explain it. It's a slightly awkward topic to cover in a very short space of time, but hopefully some of these keywords will give you stuff to look up afterwards. So here, methods are not functions. Here we're accessing send SMS on the client class, and you'll see we get a function. It doesn't say method, it says function. Some of this terminology changed with Python 3 as well versus Python 2. But if we access send SMS on the instance that we created, my client, we get this thing called a bound method on, and then it's kind of printing out the details of my client instance. So that's kind of interesting. And I'm going to have a little detour now about Python 3 specifically. So we have this new dunder variable in Python 3, which you can only use inside a method, and it gives you back a reference to the class that the method was defined on. It's a little bit magic, well, hence dunder, the double underscore at the beginning and the end. The reason for this is in Python 2, if anybody remembers Python 2, I mean, it was so long ago. When we called super, we had to pass in the instance explicitly as well as the class that we were on. And in Python 3, we didn't want to do that, but we also didn't want to break the object model in Python 3. So what they did was they came up with this magic dunder class value, which is sort of provided to methods automatically. And then what happens is, so here we can call super without any arguments. This is valid Python 3 code. But when the interpreter parses your code, anytime it finds something that looks a bit like a call to super, it then rewrites it and passes in the self parameter, self argument, and this magic dunder class argument, which is kind of part of the execution model. What's worth noting about this is if you were to assign the built-in super method, super function, to another name or something like that, there's chances that the interpreter might not catch it. It might not realize that it's a call to super in certain cases, and then it might not rewrite it, and so you might get weird. I don't know why you'd be reassigning super to something else, but there's always weird things that people do. But that was just interesting when I found it out. So we're going to go back to methods and functions. So we're going to talk about the Descriptor Protocol. Who here has heard of the Descriptor Protocol? Yes, this is good. A whole load of people are going to learn about the Descriptor Protocol for the first time. So I've really broken this down into just the bit that affects methods and functions. It's a bit more complex than this, but I have a paraphrasing of the bit that's relevant to us. And I'll break it down in a moment, so it's not just a wall of text. When we access a class attribute via an instance, if the attribute defines this magic method called dunderget, that will be called with the instance passed into it as an argument, and the result will be returned instead of the attribute that you're kind of accessing. So it's a way of making an attribute access execute code. This is actually the way that the property decorator, the static method decorator, and the class method decorator all work. They do some stuff behind the scenes to change the arguments before they're passed into the function. So just to give you a worked example, it's a little bit silly, but here we have a class, and we have a class attribute called URL. It happens to be a string. We're going to pretend that it's like a magic string. So here's what happens when you access, and we've created an instance of our client class. That's quite important, because you need to access it through the instance. So here, we've got our myURL instance, we've got our client instance, and we're accessing URL on it. Now, the first thing Python does as it's going to get this attribute is it says, this URL thing, before I return it, does it implement dunderget? And let's pretend it does. If it does, it will call that method with the instance and the class, and then it will return the result. So I'm not sure this diagram is as helpful as I thought it was when I drew it, but I'm going to go through it anyway. So we've got our client class, our send method SMS function, which defines get. All functions in Python define dunderget. They are descriptors, which means that when you try and access through the instance, I've got this kind of rewritten version here, client.sendSMS.dunderget. It returns one of these bound method objects. It creates one on the fly, which has a reference to my client and a reference to send SMS. So this is the instance, and that's the function we want to call. So it has all the information it needs. That is a callable object that it's returning you, the method. So when you call it, it's basically calling that block of code at the bottom in red, and then it's calling it without self. So this is what we were complaining about before, right? We're calling the method without self. Self magically appears. The reason is our bound method already has a reference to my client, because it was passed that as part of getting the attribute. Okay, here we go. You're going to get to see my notes. That's going to be embarrassing. I have the word click in there every time I'm supposed to press this button. So callable objects are how we can create objects that look like functions. So we do that by defining a class with a dunder call method. Basically, that is just a function definition. All the arguments apart from self become the arguments that need to be passed into the instance. But here you can see we've got a counter, which just keeps a value between calls, and we instantiate it, and then we can call the instance each time as if it was a function. But in fact, it's an instance of a counter class. Those can be kind of cool if you have an object that needs to maintain state, but really only has one operation you ever need to conduct on it. Whoa. That didn't do what I hoped it would do. Callable objects. No. Yeah. How are we doing for time? 5 minutes. Okay. We can inspect functions as well. Functions have a signature, which consists of, at the very least, the arguments that can be the parameters that are defined on the function. We can inspect them by using the inspect module. This is very small. Can everybody read that? Is that okay? Cool. Yeah, nobody wants me to touch this the window. So in this case, we import inspect, we call signature on inspect, and that passes us back a signature object. Inside the signature object, we have a bunch of information about the function, including this parameters list. So it's actually an ordered dict, but that then has it describes that X parameter. I mean, there's not a lot in there because, to be honest, our function definition isn't very complicated. So all we've put in a placeholder is called X and Y. Excuse me. When we add type hints, which I know are a controversial thing in Python, but I'm starting to really quite like them, have to admit. So here we've changed the definition so that the parameters have types associated with them. That doesn't change the running of the program at all, but you can run tools like MyPy across the code base, which will tell you if your code path involves passing strings to your function or something like that. So if we call signature on this, you can see our you may be able to see our parameters at the bottom. Each of these parameter objects in the dictionary actually contain the information that should be an int. You can also get out the default values. As I mentioned before, it's part of the function definition, and you can inspect it using the inspect module. So if you actually, for whatever reason, wanted to change the default value that was assigned to a function, you could modify it using this, or at least, sorry, access it. I'm not entirely certain you can modify it. You can do some interesting things with those signature objects, like bind a bunch of arguments to it. So here, this is a bit like that call earlier, where we were unpacking a tuple of positional arguments and some named arguments. And what that gives you back is I forget the name of the object. It's something like a bound signature or a bound parameters object. But we can access them by name now. So even though the sender argument wasn't provided by name, it was provided by position, we can just extract it as a name. So it's quite an interesting way of allowing the rules of a function definition, of a kind of parameter definition, to be turned into almost a dictionary of data. And we could use that to create automatic API bindings or something like that, that automatically kind of extracted the values we were expecting from, say, a REST API call, validated them against the type they were supposed to be, and then was passed through to the function. There's some really interesting things I think you can do with this. Here's an interesting thing you can do with that I don't recommend doing. So there's an enforce library that I came across. If this didn't exist already, I was going to write this. So the nice thing as a Python developer, from a Python developer's perspective, of liking dynamic languages where you can swap out types without any consequence and things like that, is that adding type definitions, type annotations to your classes and function calls and things doesn't have any effect on your running code, as I just mentioned. But if you wanted it to, you could use this enforce library. I'm trying to think whether it actually, oh yeah, no it doesn't. It provides a decorator that you can apply to functions that will then use that signature information to validate the types of everything being passed into it. So it can give you runtime errors when you pass the wrong types into functions. I don't know if there's actually a practical use for it, but it was kind of interesting. So I looked up the official list of attributes on functions. I quite like running dir on various objects inside Python and then seeing what devious stuff I can do with them. In this case, the one that jumped out, which you probably can't read there, is the dunder code attribute. So every function, as well as having dunder get, as mentioned earlier, also has dunder code on it. And that is a code object containing compiled function bytecode. And if you use the dis module, you can disassemble that bytecode, and then you can modify it in place. You can reassemble it again, and then you can assign it back into that. It's a mutable variable, so you can modify the way functions actually behave just by adding a decorator to the top of it. And a friend of mine's done this. So this guy, Sebastian, has written, this went mad on Hacker News a couple of years ago. And you can download and install it. The code is kind of cryptic. Well, it's not cryptic, it's just much cleverer than I am. And I've been trying to modify it to do something evil that I want to do, but I haven't managed it yet. But what this provides is a decorator that you can decorate a function with. And then it allows you to put labels and goto statements inside the function. So here we have a label called .begin, and then we've got a goto, which will jump back to label again when it hits that goto statement. The way this works is that this is actually valid Python syntax. So label.begin, even though it's got a space in there, if you imagine the space was removed, that's an attribute access on a label variable. The fact we don't have a label variable is entirely irrelevant. Python doesn't understand that until it runs the code. And the same with the goto statement, that's just an attribute access. The magic happens with goto decorator, which disassembles the code object in the function, finds these accesses on the local variable called label and goto, and then modifies with the bytecode to allow the control flow to jump around within the function. It's utterly evil, but like really, really clever. So there's obviously a lot you can do with functions, and there's a lot that makes up functions. We have an extremely flexible syntax with functions, which is really the reason for me giving this talk in the first place. So I hope you enjoyed it, and I hope you'll agree with me that functions are kind of complex. Thank you very much.